Okay, and next speaker is Jan.
Mm-hmm.
And once again, another space debris talk. Okay,
exactly,
Jan, thank you.
Thanks for the introduction. So yeah, I'm starting with the outline first, which is again a presentation which is split in two parts. The first part is about the ESA efforts on reducing the impact on astronomy. And the second part is a little bit of lessons learned from our collision avoidance operations that could be useful for this community when planning or when scheduling observations and avoiding interference with satellites. A quick overview of our office. So I work in the space safety program, and there's several different offices. What is relevant here is I'm working in a space debris office, but that means we try to find debris, we try to predict debris, and then there's the planetary defense office, which of course they're also affected by it more, but they're interested in other objects. And then there's the clean space office, which developed the technology to increase, let's say, space debris mitigation. History about space debris mitigation, which is the first topic. This is a lot of text, you don't have to read it. What is important is the timeline. So in the 90s, the IDC was established, the Interagency Debris Coordination Committee, to deal with the space debris problem, essentially, and they drafted the space debris mitigation guidelines in 2002. And all the simulations that led to that were in the 90s, right? These mitigation requirements, for example, the famous 25-year rule, then let's say, were adopted in lots of standards, or the ISO standard, but also in national laws and regulations. So this basically evolved over time, and now in this year we want to start with the ESA zero debris approach, and I'm going to give you some more feedback, or let's say context about that. A quick recap about the IDC, because there are some similarities to this forum. It's an intergovernmental forum, which means that all the agencies send delegates to this, and they perform the simulations, the modeling, to understand the space debris environment and to understand how we mitigate or how we reduce the chances that it basically evolves in an exponential way. And they are deriving these mitigation requirements and then formulating this in the documents that are listed at the bottom. And for example, this 25-year rule is written in this document. Now, remembering the slide before with the history, when we did these simulations, or my older colleagues did these simulations, it was in the 90s. And if you look at the launch traffic over the years, you see that during the 90s, we had mostly civil agencies launching a few satellites per year, and now, and we derived this, let's say, 25 years, for example, or all the other requirements, not with putting the finger in the sky, but just by simulation. So we predicted the evolution, and then it was some kind of compromise solution of finding, okay, how can we stabilize the space debris environment? And you see the propagation here, the dark blue curves on the right side. You see that it kind of stays in reasonable, let's say, domains. Well, if we repeat this simulation nowadays with the increased launch traffic that you see in 2021, you see the light blue curve, which may give you a hint that maybe the requirements that we defined in the 90s are not applicable today anymore, because the situation has changed a lot. And that's why we come up with the zero debris approach. Here you have basically the same curve as before, but projected with different mitigation measures. So for example, the success rate of the post-mission disposal rate, you reduce the decay time, so for example, from 25 years to 5 years, and you see the impact on the environment. And here the environment, let's say, is not just the number of objects, but actually a scaled index, which is not important, but you get the magnitude difference there. And what this essentially means is writing down new requirements, right? And that's what's going to happen, or that's what already happened, and will be implemented in a policy this year, which means it becomes applicable to ESA missions. And now, important for this community, there's lots of aspects in this mitigation requirements. There's the applicable orbits. We will go to also cislunar space, not only LEO and GEO. There's more protected regions. We will change, for example, the need for the success rate for post-mission disposal. We will change and update the number of years that you're allowed to stay in orbit after the lifetime. And we will add a component on dark and quiet skies. And that's, I think, the one that is interesting here. How do we assess this? Currently, there's software available. Our software is called Drama, but there's a similar one from NASA. And while designing the mission, you can already assess the impact of your mission, or how far your mission is compliant with the space debris mitigation requirements. So you can, for example, analyze the amount of collision avoidance maneuvers that you need in order to scale the fuel budget on your spacecraft. You can already analyze the required delta V that you need in order for a successful re-entry or let's say, burn-up maneuver. And you can also assess how much, let's say, you can perform a survivability analysis. So how much casualty risk I create on ground with my mission if it re-enters in an uncontrolled way. And that's a whole set of tools that are all in one software, which has a worldwide license, so not only ESA member states, and you can use. And this year we want to publish a new version. This version will be, a modern interface, but also it will have some kind of check against the current regulations and standards. And it will have a new module, which is important for this community, which is that you are able to model complex spacecraft and determine the brightness and RCS distribution. It's an approximate thing, it's just to assess it while designing the mission. It's not only for mitigating, let's say, the light pollution, it's also for us to actually see if it's trackable, because for our purpose, also for collision avoidance, we need to see the object. So the RCS should be large, the radar system should be able to track it, it should have maybe retroreflectors on board so the laser systems can see it, but for you it should be dark. So that's the thing that this module will be able to calculate. What is important is we need requirements. It's an annoying topic because it's always difficult to combine all the different requirements from different instruments, but we need requirements to put it in there. Otherwise, I mean, right now, of course, we have the 7 magnitude one for Starlink satellites from the Rubin Observatory, but we need to collect more and we have to have justified ones to put it in there. Stop. Next topic is the collision avoidance. And here I'm going to give you a quick introduction. Collision avoidance for us is our routine business. We have to perform maneuvers approximately once every 3 months for a typical mission. What you see here is the blue bars is actually whenever we escalate an event, whenever a risk is above a threshold, we have to already create work, right? And then the blue one is when we actually then perform the maneuver. Fuel is actually not a problem for us, so the cost there is not an issue, but the science loss, which is difficult to put in numbers, but in the end we have to switch off instruments on board, we have to do slew maneuvers and so on. So that's something we are, let's say, care about, and that's something that we lose eventually due to collision avoidance. If you remember the previous slide with the evolution of launches, so there's now more and more commercial players and more satellites in orbits that are operational, and that also changes our conjunction events. So on this chart, the light blue color bars, they indicate conjunction with debris. And typically when you have a conjunction with the debris, it's your duty to avoid the collision, right? But now the dark blue color, that's conjunction with constellations and other operational spacecraft. So nowadays, starting from 2021, we mostly maneuver against other operational satellites, which means we have to coordinate. And now comes the scary part, we coordinate by email, right? We search online who's the operator, and then we find out, and then you write, and then okay, who's maneuvering? No, we don't maneuver in the same direction, otherwise we hit again. And that's the current situation. It's the Wild West, basically. What we do already is we are uploading ephemeris files. We upload our predictions of our orbits with our maneuver plans. And some other operators do the same. And they're published, for example, on spacetrack.org, where some of you may download the TLEs. And then the same platform is screening it. They check if there's any conjunction between our predicted maneuvers and theirs. So there's a take-home message maybe also for the tools that you're developing, etc., right? But that's just assessing, okay, this ephemeris is okay or not against the other ephemeris files. But then once we want to, let's say, optimize our maneuver plan and avoid them, we can also download the ephemeris files and do this on our own, let's say, hardware. We are developing in our space safety program new platforms where you can better share the data, but none of that is, let's say, as established as spacetrack.org. Some warning also, because I heard some accuracy figures in the previous days, like 1 arc second and so on. When we perform a maneuver, we don't really know the pointing of our thruster, and we don't really know the magnitude. So there's always a few % of error. And if you then propagate after this maneuver, this few % of error accumulates to a much larger error of many kilometers. So whenever there's maneuvers in the trajectory, even if you have the most precise data and you observe it all the time, you will have a large uncertainty that you have to deal with. There will not be a perfect ephemeris file. Same about drag. If we are in low altitudes, and we cannot perfectly model the solar and geomagnetic activity in the next days. It's so far, science is not advanced so much. So there's always a large uncertainty for our low-flying missions, also kilometers, even tens of kilometers if it's a couple of days. And even if you have the best global network and GPS on board, that's just your limitation that you have. So you have to deal with uncertainties. And for us, this is, for example, exemplified in our number of events. So in this case, an event is whenever some collision probability is above the threshold of 10 to the power of -4. And you see that the closer you get to the time of closest approach, so when these objects might collide, the less events you have. So for us, it's actually advantageous to wait as long as possible to make the decision, right? And that's also what we do usually. Now, to summarize, we saw that the guidelines that have been developed from, let's say, scientific simulations found their way into national laws and policies. We sometimes call this the age of soft laws because there's no news on space laws, maybe because of the geopolitical situation. But at least in national laws and regulations, there are mitigation requirements that derived from this IADC one. You can assess this with our tools and also in the future, also including the brightness estimation. And for the second part, collision avoidance, there are limitations on the accuracy that you can expect. And the data sharing is key also for you. And with that, I close my presentation. Thanks a lot.
Thank you very much. We are running late, and so I will postpone any questions to the Slack
That's fine.
channel, and there's already some there for you.
Okay, perfect.